Alright, so this is the exercise that you can try to do it, and we can do this together now. So figure Q5.1 shows a data path unit of a digital system. Write a Verilog code modeling the DU data path unit such that each circuit block is identified by the dotted line is instantiated from submodule of register and subtractor. So this one you need to have a subtractor, but I forgot to have a dotted liners. So let's create the liners first. Okay. So means that this part this part, and we have this another one. We have this is another one. All right, so we have something like this where this is the dotted line and this is the register. This is another register. This is the subtractor. All right, so what the question one is that you need to create the block here inside the dotted liners here separately, and you need to instantiate this into the top module here. Means that we will use the hierarchical design modeling to do that and instantiate the design into this part. So can we do that? Yes, of course we can. Right. So let's do that, where we need to have the design here. So let's, for example, let's name this as example 5, 3. We need to create the register. And just name it as rec. What is the size? 4-bit. So rec 4. And so we create a register to represent this. So it should be very fast, where we can have the module and we can have the name rec 4. clock reset LD, and let's have a general one, call it LD instead of LDA, because we will use this one for this one also, so use LD. The input is D, the output is Q for this register. So we have input, all are 1 bit. We have input that is 4 bit, D, and we have output, and this is right, 4 bit, and this is Q. So to define that register is easy. With is it positive H? Yes, positive H. Positive reset. If reset, so the output Q should be equal to 0. Else, if, because we have LD, so if LD equal to 1, so Q should be equal to D, right? That's it, to D. So no need to have else here, because remember, if we have else, so it should be something like this. So it's no need in Verilog. Okay, so that is our register, and we can use this one for here and for here also, so it should be the same. So just save and synthesize. We have error. Why error? If oh, we don't have this. Oh, here don't need to have this, right? Okay, we don't have. So now done. This is a register. Another one is the subtractor. So this subtractor is we can use the I think we can use the new one also. Okay, we can use the subtractor. We can use our previous design, or we can create a new one. Here, let's create a new one. And this subtractor, we have A, B, and the output is we can call it F or ALU, doesn't matter. In this case, X, Y. we have X, Y, and the output we call it ALU or call it F, and input 4-bit, X, Y, okay, output 4-bit, F, and you have many options. In this case, let's make it simple where we can use the internal library. So we use the internal library. So we can have assign f equal to x minus y. So with this, the Verilog compiler will create the subtractor for us. Okay, it should be done. Right, done. So we have our submodule, and now we want to create this. So again, we need this. Here, and we want to write the code. Create a new project. I have a new folder. Okay, let's name this. And we have the file that we want to use in our design, which is one is the subtractor, another one is the register for. This is the auto. We change to make it the same device. Okay, this. Now we have clock, we have reset, we have here, look at here. We have this A0, B0, we have SEL A in, SEL A in, we have SEL B in, we have A0, B0. Let's have the control signal first. We have LDA, we have LDB, we have SELA, we have SELB, and we have A0, B0, A0, B0. Okay, done. Any other signal that we missed? No. Input. We have here all are 1-bit input, so we can just copy, paste. 1 bit. Okay, 1 bit. Have output, which is do we have any output? In this case, we don't have any output. So we have this ALU is red. We have another input actually, A1 and A0 and B0. So this is these are 4-bit 0, and we have this ALU 4-bit, right? And we have the input for this. We need to have a label here because we want to create this multiplexer, and also we want to create this multiplexer, and also we want to create this multiplexer. All right. So we can have this as a wire. Name this as A in, B in. This is A in. This one the name is A in. This one is B in. And the output for this one, we name this as right. We have name already, so this one is X in. This one is Y in. Right, and the size is 4-bit. So we have A in, we have B in, X in, and Y in. And we should have this rec A and rec B. For these two, rec A, rec B. Okay, that's it. Now we want to create this multiplexer, or you can instantiate from the previous module, right? And remember, we do this way because the question asks to do this way, where we need to instantiate from submodule. All right. Later, I will show you how we create this one in one Verilog code or in one module. So, but before that, let's answer this question first. Okay. So we can use assign keyword to create this multiplexer. Assign A in equal to this, SEL A in. If 1 is 0, if 0 is ALU. So this is the first multiplexer for this one. For this one, the second multiplexer. So you can actually use this, copy, and you have B in, and this one is cell B in, right? Cell B in, and you have B0, B0, and you have ALU here, the same. What about this? This one is X in. What about this? SELA. And if 1 is rect A, if 0 is rect B, right? And this one is Y in. Select B, select B, and if 1 is rect B, and if 0 is here, rect A, done. So all the 4 multiplexer we have already, and now we want to instantiate the register that we have. So we need to have this register, which is this one, and the name is this, and we call it rect A. Rect A has a name already, we cannot use, so let's say RA, and this is the sequence, but now the name here is not LD but LDA. All right, we use LDA, it's connect to LD, so this one is LDA, so this one should be LDA. D is this A in, so it should be A in, and the output is rect A. Output here is rect A, so that should be the first register, and the second register will be this rect B, so you can copy and paste, and rect 4, now we call it rect RB for this one, and same clock, same reset, but this one is LDB, and this one is B in, and this one is rect B. Done for that. Now we instantiate the subtractor. So the subtractor that we have is this. So the name is this, and let's name this sub, and the what is inside, we have XYF, but now not X, but in this case is X in, so it should be X in, Y is Y in, F is should be ALU, right? So the ALU cannot be right, right? So the ALU in this case is all must be ALU, rect A, rect B, rect C, all should be wire, not rect, right? So it should be the same. So we can combine. Done. and module. That's it. And let's see whether it is correct or not. Okay, we have one error, and we forgot the semicolon here. This one is not declared SEL. I think the name is lowercase. So remember, Verilog is case sensitive. So if you use small case here, make sure that you use small case. We have many warning, 18, which is not good. Not good. So all of this is that do not drive logic, means that this is not connected. This warning is actually means that something wrong with our design, and the warning says clearly that here the no output is dependent on clock, on reset, and so on. Or okay, or maybe I just find out what is the problem. Yes, because we don't have output here. So let's for example, we have ALU here is connected to the output as well. So it should solve the problem because we don't have any output. That's why there is no output dependent on clock or whatsoever, right? So the ALU, where is the ALU in this case? Here, instead of we set this as a wire, we have output ALU, and we save. Let's see whether we have the warning or not. Yes. Yeah, port list. Yeah, we solved that problem already. Yes. So the problem is that we based on the design, we don't have any output to the ALU. So now we have the output to the ALU already, then should be okay now. Right, so this is the design. This is actually correct. No problem. Now let's have the dashband so that we can see the output of this. But before that, we need to again, if we want to create the dashband, we want to see the content of register A, register B, right? So we can have include register A and register B in our output list as well, so that we can see in simulation. Right? Okay. So we have this. So now we can create the dashband. Right? So I don't want to waste time here. So I have the example of the dashband. So maybe we can use that one. So writing the test pen need skill also, yeah, because you need to design at what time the signal must be activated, right? So this is the example that you can use, and try to go back and try to study this, right? So in this case, we name this as this, and the name for this is a little bit different here. So change this to this one, name the UT. Is it the same? Clock reset, SALA in, SLB in, LDA, LDB, so A0, B0, ALU. We have another one, ALU here. Okay. And should be done here. Save. Okay, looks good. And try to do simulation here. So here we simulate the data path of our design. So let's make this as a unsigned and see whether the result is correct or not. So this is A0, B0. We set from here to be 2 and 4. So and here we LDA, we load LDB, LDA both are equal to 1, means that we load 2 and 4, right? A0 is 2, B0 is 4 into register rack A and rack B here, 2 and 4, 2 and 4. So we load here, and the next clock, what we do is that based on the data path, based on the test bench, what we do is we want to test this, yeah, rack B minus rack A. Okay, based on our design here, we want to have the output here, save back to rack B, right? So this rack B minus rack A, and the value, the result is saved in rack B. So this minus this and save at B. So we expect the answer should be 4 minus 2, which is 2 in rack B. So we can see that we have 4, 2, B minus A, right? B minus A, 4 minus 2, we have 2 here. So this is correct, 2. And next we want to test B minus B. So here B, we have 2. We minus with B, 2 minus 2, we have 0, which is correct in this case. And the next one, we load a new value into A0 and B0. So we load 5 and 3. So 5 and 3. So we have a new value in A and B, 5, 3. And what we do is A minus A. So A minus A, because A we have 5. 5 minus 5, we have 0, which is correct. And the last one, what we want to do is 0, rect A minus B. So A minus B, A we have 5, minus what we have in B is 3. Right, 5 minus B, we have 2. This is correct. So it looks like the our design is correct based on the simulation. Okay, so that is how we answer this question. Okay, where we instantiate the submodule. The submodule is the submodule of the module of register, 4-bit register here, and this one also the 4-bit register, and the subtractor here, right? Where we have created this. Yeah, we have here. See, we have register rect 4 for RA, RB, and the subtractor instantiation. Yeah. So this is another method of designing the digital circuit, where if we have the smaller module, we can instantiate our module, our submodule in the new module here. And now I want to show you how to create this or write the Verilog code for this without instantiate the submodule. Means that we write or describe this circuit. We describe this circuit in uh, in Verilog in one module, right? So let's do that. Again, we need to have the this, and let's see how to do that. Of course, we need to create a new project. Okay, just the same folder, but this one we call this data path 53. Oh, we have already data path 53. 53 number 2. And don't have file to add now. Have the new project file, module, file name, and again we need this. Okay, let's do this. We have, of course, the clock, the reset, the all the control signals, SELA in, SELB in for these two marks. And we have LDA, we have LDA, we have LDB, we have this SELA, we have SELB, and we have any other control signal? No, we don't have anymore. We have A0 input, we have B0, another input here, A0, B0, and we have ALU. And let's say we have rack A and rack B also for simulation. Remember, do this rack A, done for all the ports. Okay, and the input will be all of this, one bit, and we have the 4-bit input, which is the A0, B0, A0, B0, 4-bit inputs, and we have the output. And of course, we need to describe using the behavioral modeling. So the output here must be defined as rack also. So this is 4-bit, rack A, rack B, and we have ALU, this, and this, and this. Okay, now anything else for the declaration? No. So let's create the register number 1 or register A. Right, and this register A, we have the multiplexer in front of it. So we know how to do that already. Can have always, and this is process clock, and reset. If reset equal to 1, so the output, which is rack A, should be equal to 0, of course. Else, if LD1, in this case LDA, if LDA, now we need to look at another signal, which is SEL in. So we have another if SEL A in. If SEL A in equal to 1, the output rack A is equal to A0. Else, should be equal to ALU. That's it for register A. And for register B, it is the same structure actually, so that's why we can just copy here from A and change the value. Register B, so we have B. Now is LDB, select B in, and here should be B, and this should be B0, and this should be B. Anything else? No, right? Should be the same. And the last one is the subtractor. right? So we have the multiplexer also, but we can include in this subtractor, right? Or you can have a separate one. So up to you. So in this example, I will include in this module, the subtractor module. So if we want to include, means that there will be many possibilities, because when we look at the connection here, x can be rect A, x also can be rect B, y can be rect B, and also y can be rect A, right? So in this case, we can have behavioral modeling, where the input for this can be rect A, rect B, and also controlled by SELA, SELB. So we can have SELA, SELB, and we have rect A and rect B. We can use case statement because we have many possibilities, and this case will depend on these two signals, SELA and SELB. So we have two signals here. We can combine using concatenate operator. So we can have cell A here, cell A, and we can have cell B here. Means that this case statement will look at these two signals, and when this 2 equal to 0, 0, or we can write like this 0, means that the output here, which is the ALU, should be equal to, if 0, 0, what is meant by 0, 0? Means that cell A equal to 0. If cell A equal to 0, the input here, x, should be rect B. So x will be rect B, and y should be, if this is 0, should be rect A. So the output at ALU must be rect B minus rect A, because this is subtractor. So that is the case. Another case is when cell A equal to 0 and cell B equal to 1. So the ALU must be equal to, okay, this is 0, still rect B, and here equal to 1, so rect B. So means that what we do is rect B minus rect B. This is second case. The third case is when we have this is 1, this one is 0. So the output here, this is 1 must be rect A, minus, if this one is 0, must be minus rect A also, yeah, 1, 0, so rect A minus rect A. And the last case is when we have both 1, 1. So the LU, the output will be, if 1, 1 means that this one is rect A, this one is rect B. So should be rect A minus rect B. Done. So do we need to have a default keyword here? No need, because we have 2 bit here and we have covered all the possibilities already, so we can end the case here. Right, done for this one, and also everything here is done already, so we can have an module and everything is done. So we save our file, and in this folder, and we try to do this, and yes, we don't have any error, and we have only one warning, and this warning is of course okay. So we have this represent this. So you can see the difference between two methods. Yeah. So for the same circuit, you can have many solution actually. So you can have your submodule register where you can use again and instantiate in a new module. And it is this one also, the subtractor, where you can have your own subtractor and you instantiate in the new module and you can get this one. And also you can create one module that has all of these components, which is this one. And now we try to simulate and see whether the output is the same with the previous one or not, right? So here we create a new attachment. So in this case, time scale. Let's name this as this. And we have GB to indicate that this is the attachment. So the name is you are free to use any name, actually. So this one is to differentiate. This is the module and this is the attachment. So the module, we have this. So we can use this, and this we change to red, and this one also we change to red, and here we change to, and now we instantiate our module, which is this one. And this is design on the test, the UT, and everything here should be the same. So we can actually reuse this, copy and paste here, should be the same. And here we can create the clock, and we use the same waveform with the previous one, where we have this already. So we can actually take this and have here, so that we can have the same output, right? And try to save this. Save, and let's see whether we have any syntax error or not. Oh yes, we have. So here we don't have this semicolon, and should be done. Okay, good. So now we this setting, name the file, and start simulation and wait for the result. Oh, we have oh, wait, we close all. Okay, close first. Try to simulate again. Okay, we have something wrong at line 12 for the dash band. So we need to go back to our dash band and see at line 12. This thing cannot be.
Dekat line 8 tu.
Yeah, why?
Line 8.
Oh, okay. This one, right? Okay. Thank you. Okay, so this one we don't want to use this. Okay, so far so good. All right. Here's the output, and change this to unsigned so that we can see. Right, we have 2. The first one is 4 minus 2. We have 2. Right, same as the previous one. Let's look at the operation that we do. The first one is rect B minus rect A, and save the result in rect B. So 4 minus 2, we have 2. This is correct. And the next operation is rect B minus rect B. So we have 2 in rect B. Minus rect B, we have 0. 2 minus 2, 0. Okay. And here we load a new value, 5, 3. So we have 5, 3, a new value. And we minus rect A minus rect A. So that in rect A we have 0, right? And we load a new value into B again, right? Where we have 3 now in B. And last one we have A minus B. A we have 5, yeah, don't change. 5 minus 3, and we have 2, the result. And this is correct. And this is exactly identical to the previous one, except that the method that we use is different, but produce the same result. Okay, so that is the right. So that is the solution for this exercise. So for next exercise, we don't have time to do this, but I have the video, the previous video for the previous class, yeah, where I will share with you the link for you to go to this video in YouTube, right? So I will share in Telegram group, right? So you can look at this and try to understand how to solve this problem. Okay, so we are at 4:54, almost 5 already, and we have finished chapter 5 already. We are in good progress, and next week we will look at chapter 6, the final chapter of this course, where we will use what we have learned in the previous chapter, right? Chapter 1, chapter 2, chapter 3, chapter 4, and here chapter 5 to do this. Let's go back to the design flow here. So today what we do is number 3, 4, 5, right? And next week we will look at the higher level of design, where we will start from the algorithm, right? We will model the design in the form of algorithm, and from the algorithm we will translate to RTL modeling, right? To RTL model, where that RTL model will be in the form of RTL notation, or what we call it an RTL code, right? So from RTL code we will create this, what we have done in chapter 5, and we get the result. Okay, so that are the things that we will learn next week or in the final chapter, and we'll summarize what we have learned in this course. And also next week I will give you the last or the final assignment for this course. Maybe next week or in the week after, yeah, depend on our progress. Okay, so I think enough for today. Any question? Okay, so if no questions, so see you next week in chapter 6. Thank you.